My voice is audible and my screen you all can see, right? Shall I start the class? Am I audible? Oh, thank you, thank you. Okay. So, welcome everyone to the class. I'll read this question. This is from GATE 2022 this year. In this question, it is given an electromagnetic pulse has a pulse width of. So, it is given to us that an electromagnetic pulse has a pulse width of 10 raised to the power minus 3 second. Okay, the uncertainty in the momentum of the corresponding photon is of the order. So uncertainty in the momentum is given to us. Okay, and the order is given where n is some integer and you need to find out the value of this n. So, first of all, we are given delta t is given to us and delta p is also given to us, right? So, from this, you know two Heisenberg uncertainty principles. One is delta E, the statement delta E into delta T is equals to h upon 4 pi, and the other one is very famous one delta P delta x is equals to h upon 4 pi, right? So this one is very famous. I mean, it is really impossible to simultaneously measure the position and the momentum of any particle, right? Suppose you are finding out then an exact value of the position of a particle, then there will be a large this uncertainty in position, sorry, momentum. So this one is very famous one. Delta P delta x is equals to h upon 4 pi. There is one more uncertainty principle, and that is this one. Delta E is into delta T is equals to h upon 4 pi. So this says within time interval delta T, like suppose there is a time interval delta T, it is impossible to measure energy precisely. If you want to measure energy precisely, then you have to increase this time delta t, right? So again, an inverse relation came for delta for energy and time also. And this delta t is defining the amount, the time taken for the measurement or anything. Sorry. So I'll again repeat, like delta x and delta p, the famous Heisenberg uncertainty principle for position and momentum. There is one more Heisenberg uncertainty principle for energy and time. So it says for a time interval delta t, it is difficult, it is not possible to precisely measure the energy of a state. If you want to precisely measure the energy of a state, you need to increase the time. So again, uncertainty in energy and time is coming just like in momentum and position. So coming back to the question, we are given delta t and delta p. So how you will do? You'll write this formula, delta e is equals to, sorry, into delta t is equals to h upon 4 pi. So do you know any relation between energy and momentum? Energy and momentum. Any relation? E is equals to under root. This is this is a relation, right? In quantum mechanics, this is a relation between energy and momentum. But this is EM wave, and EM wave is a what is EM wave? Sorry, wave. EM waves are moving photon, right? And what is the rest mass of photon? What is the rest mass of photon? It's zero. Rest mass of photon is zero. Okay, put m not zero in in this formula. So E is equals to under root p square c square. E is equals to p c. Okay, this is the formula. E is equals to p c. So now here you can replace delta E by pc, right? Delta t is equals to h upon 4 pi. Okay, so we are given p, delta p, we are given 10 raised to the power minus n. C is given, C is 3 into 10 raised to the power 8. Delta t is given to us how much? 10 raised to power minus 3. H 6.6 into 10 raised to the power minus 34, and 4 into 3.14. So can you all calculate it how much it is coming? 10 raised to the power minus n is equals to 6.6, 10 raised to power minus 34. This will be L taking just, I'm just taking approximation. So this is 4 and this I'm taking 3. So it is 12. Okay. I'm just taking rough value of these. So 12 into 3, 36. 36 into 10 raised to the power 5. So this will go above 6.6 upon 36. So it will give 10 raised to the power how much? Minus 39. It is less than 1, right? I'll write here. So 6.6 divided by 36 into 10 raised to the power minus 39. You can see this one is less than 1. Okay. So just take this dot right side. So 66, 36 is equals to 10 raised to the power minus 40, right? Right. So it will give you a value around 1 point something. So into 10 raised to the power minus 40. So what will be the value of n? What will be the value of n? It will be minus 40. Got it? I'll again do the question for every one of you, those who have joined late. So, in the question, we are given to us an electromagnetic pulse has a pulse width of 10 raised to the power minus 3 second. The uncertainty in the momentum of the corresponding photon is of the order this much. And now n is an integer, and we are asked to find out the value of this n. So we are given delta t and we are given delta p. So there are two Heisenberg uncertainty principal relation, and each containing this delta t and delta p respectively. One is delta E into delta t is equals to h upon 4 pi, and the other one is delta p into delta x is equals to h upon 4 pi. So these both define uncertainty. If you are going to find out the exact position, you will get a large amount of uncertainty in the momentum of a particle. And if you want to measure the energy of a system in a particular time delta t, you cannot measure it. So to precisely measure the energy of a particular system, you have to increase the time. Okay. Now coming back to the question, in question we are asked to find out n integer value. So use this delta E into delta t is equals to h upon 4 pi uncertainty formula, and replace E by pc. Why pc? Because in because there is a relationship between energy and a momentum, and that is under root p square c square plus m naught square c4. This is total energy, this define kinetic energy, and this is rest mass energy. So for photon, rest mass is 0, so E is equals to pc. Okay, put pc here. P value is given to us, C value is given to us, delta T value is given to us, is equals to H upon 4 pi. H value is given to us, 4 into 3.4. Just do the simple calculation and you will get your N value. Okay. If suppose, I think it's correct. Got it, everyone? Shall I move to the next question? Okay. This value can also come 10 raised to the power minus 39. If you see 6.6 divided by 36, if you see, then it will come 66, 360. It will come point 0 something, 0 point, okay, 2 into 10 raised to power minus 39. So in the, when I saw the solution sheet in which it was given, it will vary from 39 to 40. But I was getting 40 as a correct answer, because if you look here, it is 1 point something and exact 10 raised to the power minus 40. So yeah, it will vary. Okay, I'm moving to the next question. Next question is from quantum mechanics. So in this question, it is given the wave function of a particle in a 1D infinite well. 1D infinite well. This is 2a is the dimension of infinite well, and particle is here. So can any one of you tell me the wave function value for an infinite, for one dimensional infinite well? What is the wave function? Like the form of wave function? Under root 2 by a sine n pi x by a, right? And the energy value is E is equals to n square pi square h cross square upon 2 ma square. This is when the dimension is a, and but in this question it is given 2a. Okay, in this question it is given 2a, right? So you see here, you are asked to find out the probability of finding the particle in n is equals to 2 state, right? So n is equals to 1, n is equals to 2. These will define states, right? And so on. So now you are asked to find out the probability of finding the particle in this state. And wave function is given to us. This is this 1 upon under root 6a root 2 sine pi x by a plus root 3 cos pi x upon 2a plus cos 3 pi x upon 2a. Now, first of all, just try to see that here it is n pi x by a. Okay, so n will define state and a will define the dimension of the well. This now, see here, if I'm multiplying it by 2, I have multiplied it by 2 in numerator and in denominator also. Okay, so match these two brackets, what all the terms inside the bracket. This 2a will define the dimension of the well, because here the dimension is 2a, and this 2 will define n is equals to 2 state, right? So you need to find out the probability of finding the particle in this state. Okay, that you will find out by multiplying by the constant that is given, that is attached with this state. Okay, this is which state? This is n is equals to 1 state. and this is n is equals to 3 state. So this wave function is a linear combination of these states. Okay, like this, right? It will go up to. Now, to find out the probability of finding the particle in this state, what you need to do, you need to just normalize this wave function and find out that it is equals to 1. It is normalized. So we will do the normalization. You know normalization, right? And this should be equal to 1, right? If you do normalization here, so you'll get 2 under root 6a. These terms, this sign term will add up to give 1, so no need to include them. This will become what, yeah, this will become root 3 upon root 6a. I'm just doing it directly because these constant will give you their square, right? 1 upon root 6a is equals to 1. This should be 1. These terms will not come. This will give this, when you will integrate it, it will give you a 1. So just take the constant that are in their front. Okay. So this will give 2 upon 6a plus plus 3 upon 6a plus 1 upon 6a is equals to 1. So there is 1a factor. So it is not normalized. It should give 1. So what you need to do, you just multiply it by a here. Okay. So there will be a square, which, so there will be a square because this is not normalized. So I have multiplied it by a. So this 1 upon a square is equals to 6 upon 6a. It will give 6 upon 6a is equals to 1. So a square will be a, and a is equals to root a. If you multiply the whole term by root a, you will get what you will get. When you will normalize this again, you will get 1, because the probability of finding the particle over all space should be 1, right? So now I'll do, should go back and forth. So this phi x is, what was there, root 2a, this will come, and root 6a sine, this is 2 pi x by 2a. I'm not writing the other terms because I know these, I don't need to find out the probability of finding the particle in n is equals to 1 and n is equals to 3 state. What I need is this one. So the factor, the constant factor with it is this. So square it, you will get the probability. This is 1 by 3, 1 by 3. Okay. So what will be the probability of finding the particle in n is, what will be the probability of finding the particle in n is equals to 2 state? 100 by 3 is how much? 33%. Okay. I'll repeat the question. I'll do the question one more time. So it was given to us that the wave function of a particle in one dimensional infinite well of size 2a at a certain time is given to us. What will be the probability of finding the particle in this state? This one. First of all, you have to normalize this wave function. Since this wave function is not normalized, so what you need to do, you need to do add, multiply it with the factor a. That factor will give you a value. Multiply whole wave function with that value, you will have a normalized wave function. And now you are asked to find out the probability of this one. Just square the term attached with this state. Okay. You know why this generally comes, like, why this generally come. So you know very well that phi, the general solution of this phi is a linear combination of these states. Okay. Now I'm writing it like this. If suppose I have to find out the probability of finding the particle in phi 1 state, so I'll again normalized it. This is phi n, this is phi m. So phi m will be phi m. Now do this. You will get what? You will get cm cm cn. This will come like uh, phi m phi n dx is equals to 1, because probability of finding it all the state probability of finding it in all the space is 1. So this is phi cn, this is cn, and this will be 1. Why 1? Because you know chronic or delta n is equals to 1 when m is equals to n, and when m is not equal to n, so it is 0. Suppose m is equals to n, so this term will give 1, and now here it is m is equals to 1, and so it will give cn square is equals to 1. Okay, so this is the probability. So similarly, if suppose this is 1, n is 1, so the probability of finding particle at stage probability of finding the particle at this for this wave function will be c1 square. Okay, and the probability of finding the particle for this state phi 2, it will be c2 square. Got it? How this 33 come and what is the logic behind it? So shall I move to the next question? Is there anyone who have doubt? Huh. Yeah, yeah. Hmm. That is not one. Where? Mhm. Okay. Actually, the logic behind these questions, like this one, this. So we generally write this term for this phi. Suppose you are given sine. So we generally write this term as a linear combination of this and try to like normalized it and find out which value, which state they are asking. So we just square the mod of the one, the factor which is written in front of it. So if this is not coming, I'll try to do it in a traditional way. This question 34. Okay, I have noted down your doubt. So I'll try to do it in the traditional way. So this is like shortcut one. Okay. Okay. I'm moving to the next question. So this is the 2021 question. This is a straight formula question. I mean, you just have to apply a formula. So do you know Coulomb energy formula? So I'll read question first. The Coulomb energy component in the binding energy of a nucleus is 18.432 MeV. If the radius of the uniform and spherical charge distribution in the nucleus is 3 Fermi, the corresponding atomic number rounded off to the nearest integer is. First of all, we should know the Coulomb energy formula. So, what is Coulomb energy formula for nuclei? The formula is 1 upon 4 pi epsilon naught 3 by 5 q square by r. This formula. I think this is the derivation in electromagnetic course also. When we have a charged sphere, we know the potential, we know the electric field, then find out the energy of the nuclei, something like in electromagnetic. So this is the derivation. And the formula that we get in the end is this formula. 1 upon 4 pi epsilon naught 3 by 5 q square by r. So 1 upon 4 pi epsilon naught 3 by 5. So you can write q square, q is equals to ze, right? Upon r. So this is 1 upon 4 pi epsilon naught e square 3 by 5 z square by r. Okay. And this value is given to us, Coulomb energy value 18.432. So 18.432 e square upon 4 pi epsilon naught is 1.44 MeV Fermi. 3 by 5 z square is a z square we need to find out, and r is 3 Fermi. This will cancel. Z square is equals to 18.432 into 5 upon 1.44. So what will be the value? Calculate it. This will come how much? This will come 64. This will come 64. So Z will be 8, right? So this will be oxygen. Z is equals to 8. Got it? This was a straightforward question of 2 marks. Now I'm moving to the next question. So try this question. Try this question, everyone. This is from nuclear and particle physics. So at least try this question. I'll give you 2 minutes, 2 to 3 minutes for you to try and tell me the answer. Like, which statement is true for X? Just read the question and tell me. I mean, answer is given like it is C. C is the answer. But why it is C? Hmm? So yeah, in this question, this question, there is a massive particle X. It decays to 2 photons. Hmm? If you see, photons are chargeless. So X should be charge is wrong because photons does not carry any charge. Now here you can see spin of X must be greater than and larger than 2. So photon I spin integral particle and spin of photon is 1. So these are 2 photons. So it will have overall spin is equals to 2. So it is given the spin of X must be greater than or equal to 2. So greater than is given. So that means it is also wrong. Now the D is X must be a baryon. So in last class, we have learnt about baryons, and we know that there are two kind of baryons and baryons resonance, right? One is 1 by 2 angular momentum half with the parity plus, and the other one is 3 by 2 positive. Okay, proton neutron comes under this, and in this some baryons come. So if any particle is a baryon, so it should have a baryon number 1. Photon is not a baryon. So suppose in left hand side we have a suppose in right hand side we have a baryon number 0. So in left hand side also we must have a baryon number 0. So this should not be a baryon. So this is also wrong. And X is a boson. Yes, X is a boson. Correct. Reason being because photon is also a boson. So that is why this one is correct. Okay. Now the next question is this one. Which one of the following conservation law is violated in the decay of this? This question. One is angular momentum. B is total lepton number. C is electric charge, and D is tau number. So I'll again ask, want you to at least attempt this question. I'll give 2 to 3 minutes again. Attempt this question and tell me what is the answer of this question. Yeah, but why D? Hmm. Hmm. And angular momentum? Angular momentum? So see, for this question, if you see, so leptons, electron, electron, neutrino, muon, muon, neutrino, tyon, tyon, and tau, sorry, tau neutrino. Okay, so these are six leptons. They have lepton number plus one. Now there are anti-leptons also. Positron, antineutrino, muon positive, fourth muon, antineutrino, fifth is tau positive, and sixth is tau antineutrino. Okay, these have lepton number minus 1. Now, if you see in this question, leptons are fermions. Leptons are fermions, right? Spin half particle. So, angular momentum is not specifically defined in this. So, if I am taking it as a spin angular momentum, because it is not mentioned. Here you can see tyon is a fermion, so spin half. Also, you can see these are These all three are spin half particle. Suppose these two spins are anti-parallel. So they will cancel each other. We are left with one this spin half particle. So in this way, left hand side is equals to right hand side for one combination. We don't know about the other combination, but if it is a multiple choice question like in this way, which one of the following conservation law is violated in the decay like this? So if in the question it is given like a, either a or b, or second option is given b or c, or third option is given, so you can consider this one. But here I'm not sure because it is not written which angular momentum they are asking, total angular momentum, linear, or spin angular momentum. So I'm considering spin here. So by spin I can say like 1 by 2 1 by 2 if they are coupling to give zero spin, and we are left with only one spin, half. So left hand side is equals to right hand side. So by this way spin sorry, angular momentum is not violated. Total lepton number. So there are lepton number for electron, there are lepton number for muon, and there is lepton number for tyon. So total lepton number is equals to le l mu plus l tau. Here L tau is equals to which one? Negative, minus 1, because it is tau positive. So lepton number will be minus 1. I should write here mu1 negative, negative, and this is yes. Huh. So yeah. So see, they are spin half particle, right? They are fermion. So for this, it is spin half. Okay, left hand side. So here also, if suppose these are three spin half particles, so two of them are coupling to give spin zero. So we are left with only this one, na? Vector addition of spin. If two are coupling to give zero, then we are left with this third one. So half. So that is why left hand side is equals to right hand side in this way. And for B, total lepton number. So there is lepton number for electron and lepton number for muon and lepton number for tyon. So total lepton number is the addition of these three. Hmm? So here we can see tyon. So tau positive has lepton number minus one. So left hand side we have total lepton number is equals to total lepton number, not individual. Total lepton number is equals to minus one. And left hand sorry, in right hand side, muon positive, positive again minus one, and this is muon negative, so this is plus one, so this will cancel, and we have l mu is equals to minus 1. So total lepton number is minus 1 on both the sides, so it is also conserved. Electric charge is conserved. So the individual tau number is not conserved. So D is the answer. So one thing is there is a conservation of total lepton number and there is a conservation of individual lepton number. So for total lepton number, you have to consider lepton number of each particle which is given to in the equation. Okay, electron, muon, and tyon. And for individual, you have to look. Okay. So now I'm done with the questions. So I'll again go back to that. Yes, tau lepton number. Tau number. Okay, tau number means lepton number of tau particle. This is tau number here. Lepton number of tau particles. Okay. So I am done from my side, but there is one girl who asked me the question. What is the name? What is your name? Can you unmute yourself? Sejal. Okay. I'll look up to your question. I'll do the question again. So you're joining my class regularly, right? Or this is your first time? Okay, this is your first time. Okay. So, if possible, can you join my class next week also? Okay. Okay. Thank you. Thank you, everyone, for joining the class. I'm uh, ending the meeting. So, thank you, everyone, again.